So this section will talk about not specific formulas, but a general understanding of H that cuts across all kinds of situations. So we compute and H correctly. So it's sort of a broad general comments over the entire chapter of the convective heat transfer coefficient and its related H calculation. How we write the formula decides the direction of the convective heat flux or heat flow that we calculate using the formula. So let's consider two identical situations. In both cases, here and here, we have Ts as surface temperature and T infinity as the bulk fluid temperature. So Ts is the surface temperature and T infinity is the bulk fluid temperature. So if I write the formula for heat flux here as H times Ts minus T infinity, and here H times T infinity minus Ts, since flux has a direction, and the direction here is from S to infinity, and then here the direction is from infinity to S. So if we write in terms of flux, S to infinity, and here infinity to S, and so they look like two different formula. This one versus this one, they're different. So one must be wrong. Actually, they're not. They both work out. How? So let's try for H equal to 50, Ts equal to 10, and T infinity equal to 30. Okay, so if I plug all that in here, TH, so 50 here, 10 here, and 30 here, then what do I get? I get here 50 equal to minus 1000. And if I do the same thing here, 30, 10, and H is 50, then I get plus 1000. So this is a plus 1000, right? So why are they both okay? And they are both giving the same answer, because this one is saying from S to infinity I have this much of heat flux, which is in watts per meter square. This is also in watts per meter square, let's say, when we have H as watts per meter square per degrees Kelvin, and this could be in degrees centigrade. And so S to infinity is negative 1000, negative 1000. That really means it's going from infinity to S as 1000. And so that is the same as on the other side. What is critical is as soon as you write the formula, as soon as you write this formula Ts minus T infinity, it immediately decides what is the direction of what you calculate. So the direction is from the first one that you write to the second one, S to infinity. And the same here. When we write T infinity minus Ts, it goes from infinity to S, and that keeps it thermodynamically consistent. Note that we did not care whether this temperature is colder or warmer. We simply follow the sense for the difference. If you write Ts minus T infinity, it's going from S to infinity, and that keeps it thermodynamically consistent. Another and perhaps the most important characteristic of H that we use is that it increases with velocity. So here we have two diagrams, one for lower velocity and lower Reynolds number. Reynolds number is related to velocity by this expression where u infinity is the velocity far away from the surface here, and so lower velocity leads to lower Reynolds number and higher velocity leads to the higher Reynolds number. At the higher velocity or the higher Reynolds number, the fluid simply, it has more energy to just blow the kind of the stagnant layer away. It has greater inertial force compared to the viscous force that is trying to make this stagnant layer stick to the surface. So in both cases, temperature goes from hot on the surface to cold in the fluid, but when the boundary layer is thinner, it goes through this temperature difference from hot to cold over a smaller distance. So the gradient, which is the temperature difference divided by the distance, since the distance is smaller in case of the higher Reynolds number, the gradient is higher. And higher gradient simply means more heat flux. So this one has a higher H. At still higher Reynolds number, the temperature values of course stay the same, but the boundary layer is even thinner, so the gradient is even higher, and so the H increases further. So if you have different types of surfaces and flow over them, H is always going to vary along the surface. Let's look at why. So let's look for a simple answer. Here we have cold fluid hitting a hot plate here. This is the heated surface. So the temperature goes from hot to cold. Now remember, H has to do with temperature gradient in the fluid. Why? Because the layer touching the surface of the fluid is at rest. So the heat has to first conduct through that layer. So if we write at the surface minus K of fluid, thermal conductivity of the fluid times temperature gradient in the y direction at y equal to 0 or surface, that's what determines the amount of heat that comes out of this surface. So it's the temperature gradient. How fast does the temperature change? Now when the cold fluid hits the surface, it at the leading edge here, it's hard to see, at the edge here it goes from hot to cold over a very short distance, which means there is a very large gradient, and that leads to high rate of heat transfer, as you can see from this equation. Now as the fluid flows over the surface, it warms up, it picks up heat. So at some point downstream here, if you can see, then the same fluid has warmed up, which means what? the temperature change in this direction is now less rapid, or the gradient has decreased, which means the rate of heat transfer from the surface to the fluid is lower down here. Now, if we look at the equation for convection, heat flux is equal to H times Ts minus T infinity. Now, these two are constants. So, when we say that the heat transfer here is lower, that just means that H must be lower over here than over here. So which means H is going to look something like that. It is very high initially when the cold fluid hits the hot plate, but it keeps dropping. So this is always true for any kind of surface. So when you see a formula for H, you should ask, is this for a location or an average over the entire distance? If you don't see a location variable in the formula, it is the average over some surface. H varies with the nature of flow, whether the flow is laminar or turbulent. H can be quite different. So let's look at how. So H can be substantially higher in turbulent flow as compared to laminar flow. So let's look at how that is possible. So let's consider this flow of cold fluid over a hot plate here. So the temperature could vary something like this, because the fluid is moving in layers in a laminar flow. Why would the fluid move in layers? It's because the viscous forces are strong in laminar flow in comparison with the inertial forces. And so the viscous forces are the stabilizing ones, and they keep the fluid nicely in layers. Now on that same plate, downstream, the viscous forces get progressively weaker compared to the inertial forces, and the flow gets more chaotic. And that's what we call a turbulent flow. So the flow is no longer as nice as in layers over here. In laminar flow, the hot layer is here and the cold layer is here. So the heat transfer in this direction is kind of nice and organized, but it is not as efficient as in the turbulent side. Why? Because in the turbulent side, then a cold layer, a cold fluid, because it's moving randomly, it can come in contact with the warmer fluid more easily because there is mixing. So the cold layer can come right down and mix with the warmer layer. So this increases the rate of heat transfer, and therefore it increases H. Now this transition depends on the critical Reynolds number. So some sort of a critical number below which we have the laminar flow and above which we have the turbulent flow, and therefore two different equations that we have to be careful. So in a given flow situation, we have to first check whether it's laminar or turbulent to decide which H equation we should use. H is not a material property. It may be obvious to some of you, but I have seen some of us thinking this way, H is another material property. First of all, what are examples of material property? Density, viscosity, these are examples of material property. And so as velocity increases in convective heat transfer, as velocity increases, Reynolds number would be increasing, and for two different Reynolds number, if we plot the boundary layers, then the boundary layer would be a lot thinner in case of the higher Reynolds number or higher velocity. It's because the inertial force increases, making this slow moving layer, that's the boundary layer, thinner, and therefore H is higher. So if H increases simply because the velocity increases, it really cannot be thought of as a material property by itself. Of course, H depends on material properties like density and viscosity, but it itself is not a property. It describes a process. It's a very complex process that is going on here with flow and heat transfer. It's quite a complex process, and we have this simple description of all of that by saying Q equal to HA Ts minus T infinity. That's just a simplification of a very complex process, and H kind of lumps all the details of the complex process. So H really describes the process or the overall effect of the process rather than being a property. So sometimes we have this confusion. We talk about conduction and convection, and H is convective heat transfer coefficient. So is conduction something on top of this? Is something separate? Remember, convection is conduction plus flow effects. Okay, so convection is flow added to conduction, and we're going to prove this by finding H for conduction only and compare that with convection when there is also flow. So to make the point that convection is really conduction plus the flow effect, I chose the problem of heat conduction into a fluid from a hot sphere, except that the fluid is not moving. How is that possible? So let's say we are in space station, so the gravity can be ignored, so there is no natural convection and there is no fan blowing on it. So the air is still, so we will only have conduction heat transfer from this sphere of radius r. So the boundary condition would be T at r equal to r is Ts, and the surrounding fluid is at temperature T infinity. So T at r goes to infinity is T infinity. Those are the two conditions for which I'm going to do just conduction heating for a sphere, so which means in a spherical coordinate system. So this would be my governing equation. So we only have the conduction term, and there is nothing else, and we're doing steady state, so that's equal to 0. So since the derivative of this is equal to 0, so then that must be equal to a constant. and if I simplify them, I get this one, and then I integrate. So C1 over R squared integrated gives me minus C1 over R plus C2. So that is my solution. Now I want to use the boundary conditions. So if I use this one, this boundary condition, t at R goes to infinity. So if I plug in R goes to infinity, then I get T infinity equal to C2, which is this one. And so if I plug that in, then I get, plug that into this equation, then C2 is T infinity. C2 is T infinity, so I get T minus T infinity equal to C1 over R. C1 is still not determined. And then I use this first boundary condition. And so I plug in for R equal to R. And so I get and for T, I plug in TS. So I get another equation from which I can eliminate C1. And so basically I plug in for C1 into this and I get this final solution. So this is how temperature varies with position R. Temperature as a function of R. So on the surface, how much heat is leaving this heated surface? So that would be minus K of fluid del T del R at R equal to R using Fourier's law. So now I plug in for T, I plug in this value, and then I get this, and del T del R, if I take the derivative, I get 1 over R squared, and then I'm going to plug in R equal to R. So finally I get this, which is simplified as this one. So this is my heat flux at surface. Okay, but using the idea of convective heat transfer coefficient, I can also write that whatever heat is leaving the surface, that I can write in terms of H as this. It's the same one. If I think in terms of a transfer coefficient, heat transfer coefficient, then I can write this. So they must be equal. So then I write Kf times Ts minus T infinity that we just derived from here over R is equal to H times Ts minus T infinity, which gives me H R over Kf is equal to 1. In other words, if I change it to diameter, then it will be HD over Kf equal to 2. So this formula gives me H for when there is no flow. So when there is no flow, it's conduction only. Conduction only H. So H for conduction only is given by this. Now if I look at the equation, let me write here again, conduction only. Then if I write the equation for natural convection over a sphere, this we have discussed separately. So natural convection over the same sphere, then I have this formula. You notice the interesting part. This formula has two parts. One is this 2 and then plus some quantity. So for natural convection, then this 2 part comes from conduction. So this conduction gives the first part, and then the flow effect, you notice it has this Grashof number that determines how strong the flow is going to be. So this part gets added because of flow. So for natural convection, when we have a flow, H is given by an equation that has this part 2 plus the flow. So this is conduction plus flow effect. So then H always includes the conduction part. It has the conduction part plus the effect of flow, and this particular formula kind of nicely makes that point. Perhaps the most fundamental concept of convection is that the rate of heat transfer in convection is higher than in conduction. So here we show that from actual calculations. So we have a hot plate here and colder fluid above it. It's fluid but not moving, so it's pure conduction heating. So as the heating starts, initially, of course, there's a big gradient from the hot to the cold fluid, so we have very high rate of heat transfer. But then the rate of heat transfer drops because the fluid here reaches or closer to the surface temperature. So the temperature gradient drops, and so the rate of heat transfer quickly drops to a much lower value in conduction. But if we bring in convection, that simply wipes out that warmer layer and keeps wiping out. It basically then maintains a thin layer, or the temperature change with this wiping effect of convection maintains a much higher gradient, going from the high value for the plate to the lower value for the fluid. It goes through this temperature change over a much smaller distance, so it's maintains much higher gradient, and therefore the heat flux increases for convection over the conduction. This is perhaps the most essential concept of convection. This higher rate of heat transfer in convection can be seen in the H formulas. So here I give an example of formulas for a sphere. So we have heat conduction, let's say from a heated sphere, in two cases, one with no flow, so it's just conduction, and the other one with a forced flow. So you have a forced flow this way over a sphere. And for these two cases, if we just look at the formulas, we can see that convection increases the rate of heat transfer. So for conduction or no flow, we derived this equation for H. By the way, this is K for fluid. And for forced convection, also we presented this formula elsewhere. It's in a new Nusselt number is HD over K fluid. Okay, so that's equal to this. So you notice that for conduction formula, this HD over KF is equal to 2. And here for forced convection, it's 2 plus something. 2 plus something that is a function of the Reynolds number, which has velocity. So higher the velocity, higher the Reynolds number. So this increases with velocity. And only when it is 0, if this part is 0, then it is equal to 2. Otherwise, it's higher than the 2 because it's 2 plus something. So then for convection, when you have convection, this part gets added. So which means for convection, the H value is going to be higher. Another way to make the main point that the rate of heat transfer in convection is higher over conduction. Finally, various flow situations or various sort of classes of flow have their characteristic range of H. So here are the typical ranges of H values for various situations, like free convection in air, forced convection in air, forced convection in water, and so on. Now, just because we provide this range doesn't mean we just pick a number from the range, because for each category there is an order of magnitude variation. Order of magnitude variation, which means if you just randomly pick a number, you could be off by a factor of 10, which is very, very significant. So we still have to go back to the formulas to get the exact values, but this gives us the relative range where we expect to get the numbers in H. But the plot does mean, for example, that forced convection is generally higher H than free convection, or water is a lot more efficient for heat transfer than air. These are both forced convection. Condensing water vapor gives the highest value of H. This is why, for example, steam burns more easily than hot water. So these just give us the general idea of what to expect in a certain type of flow situation before we do the detailed calculation.